Previously on the OS.
So there are different options here, and actually several of these that you have described here are actual scheduling algorithms that we are using in operating systems.
Yes.
And this is exactly the case that I wanted to talk about. Schedule the shortest job first. What would that look like if we take the previous picture with the 5 tasks? We would schedule it this way. It's a round robin, it's a compromise. But a compromise can be the best thing sometimes. MFQ has multiple queues and they are ordered by priority. And each of these queues is a round robin queue. Deadlocks. First is the mutual exclusion condition, the hold and wait condition, process no preemption condition, resource circular wait condition. You could number mutexes. You could provide global numbering for all resources. And this is a strategy that you will definitely use in the practical. Also with two-phase locking, we are again going back to this try again loop. In X3 we have 3 levels of journals. We have X4 is the successor of X3, and see you next week for the presentation of assignment.
Operating systems done, far from where we started from. Operating systems done.
Okay, welcome to the last lecture of operating systems, and today we are going to talk about operating systems assignment 2. I just realized that I might want to adjust the camera just a bit, so like this. Yes, that's better. And today we are going to work on some slides together, especially at the beginning, and we will go through all the topics of assignment 2. Okay, let me just select the slides. Okay, I can also see them. Okay, let's talk about the topics. The topics for assignment 2. What we will talk about today are the mandatory topics: virtual memory, copy on write, swapping, but also we will talk about shared memory, we will talk about memory mapped I/O, and dynamic memory in the user space, Malloc for instance. Now I also see that the chat is also a bit small. Let's maybe zoom in on the chat a bit so that you can actually see when your message is received in the chat. And maybe I should also disable this filter here. Yes. Okay, that works better. Okay. Other topics that we will discuss today. Well, you can basically do anything that is operating systems related. That's the same as before, as for assignment 1. Anything that is operating systems related can be done, especially if it's in the kernel. It's very likely that we would give you points for that. To make sure that you don't invest time on something that doesn't give you any points, just ask your tutor or me whether something will give you points. The first topic that we are going to talk today about is page replacement, swapping. That's a big topic of assignment 2 and probably the topic where you can gain most of the points. Swapping is basically very simple. You swap pages from the RAM to the disk and keep them there. The important part here is don't forget to lock shared resources, and you see that I highlighted this one. This is a hot topic in assignment 2 because suddenly you have to lock everything and it becomes all very complicated to lock everything properly. What does the operating system need to know to swap? And I prepared a Menti for that. So if you haven't joined the Menti yet, you find the link down there in the description, but you can also join using this code, and I will directly jump onto the first Okay. Why was this tutorial moved time-wise without updating the calendar or announced via email? I'm not sure that whether this was moved. I think this was the time slot that I scheduled in the beginning of the lecture. I'm not sure whether anything was moved around there. I might be that it's an exam week this week. If so, some of the appointments were cancelled without telling the lecturers, and then I wouldn't know whether there was anything cancelled. Can we make an address translation example today slowly? Would help very much. We already did that last time. We are not doing that today, because the exercise interviews are already running, and you probably, it would not be fair to now provide you with an explanation where others already had the exercise interview. So the time for that was last week, where I offered also a special tutorial section, not this week. But let's start with the brainstorming. What does the operating system need to know to swap pages from RAM to the disk? What do you need to know so that you can do that? Everything. That's not very specific, right? Okay. Memory size. Yes, how much memory do we have? Yeah. The relevance of data. Yeah, probably all the data is relevant. Processes which reference the data, the physical page number and the virtual page number. Where is which page? So this is interesting. Where is the page? And there we have to think about two things: the RAM and the disk. Where is it in the RAM and where is it in the disk? On the disk. Probably not at both locations at the same time, but we somehow have to find it. And this information has to be stored somewhere, because the operating system needs to know. The operating system needs to know where the disk is, where on the disk a page is, and you need to store this information somewhere. What else? Well, you're managing a disk now. How do you know where to place things on the disk? How do you know whether a page is swapped or whether it is in RAM? The disk driver probably won't tell us where things are free on the disk. The disk size, yes, is probably relevant, but we still don't know where on the disk exactly a spot is free for our page. And also, when the page is swapped out, where is it swapped? Okay, so we already have some ideas here. I also put them on the slides so that if you download the slides later on, you also have these questions back here, the brainstorming questions. And basically you can imagine it like this. You have some user processes, some kernel here, and there's some mapping from virtual addresses to physical addresses, maybe these physical pages. But in some cases now this can also go to, it's called here virtual memory. We're thinking of swapped memory here, swap device, and maybe we have a swap manager class for that. And there are also, similar as for the page manager, we have also information whether this location is in use or not. Okay. Let's talk about page faults. So there's some part of this in this flow chart. I think you all will like flow charts, and some part of this flow chart is already implemented, some part is still missing. Let's go through this step by step. We start here with the page fault, and the first thing that we check is whether the page is present or not. If it's present, well then maybe it's a copy on write page fault. Otherwise, maybe something has gone wrong. Maybe it's a page that you are trying to write to, but it's a read-only page. So there might be some errors here, or it's copy on write if you already have implemented it. Otherwise, if it's not present, then the question is, where does this address, where does this address, or from where is this address accessed? Is it from kernel? The kernel, would the kernel access memory locations that are not present? Maybe, it depends on how you implemented it. But in the most general case where we want to implement swapping, we will go through this path, user space, and then the question is this even a valid address for the current thread, for the current process if you implemented the process abstraction. The basic swap doesn't have this. If it's not a valid address for this process or thread, then we can terminate this process or thread. If it is a valid address, but somehow it's not present yet, then we have to do something about that. Maybe we have to load it from the binary, right? But in other cases, and this is already implemented, but in other cases, we have to load it from the swap disk, and this is not implemented yet. So if the page was there before and if it's now on the swap device, then we will go here, check, do we find this page in the swap device? If we don't find it there, then that was a problem, right? Then we have a bug in our operating system. If the page is swapped, but you can't find it on the swap device, that's a bug. But if you can find it on the swap device, then of course you have to load it back into memory. And then the question is there a page free in the physical memory? Can we load it into the memory? If we can't, then we have to invoke the page replacement algorithm to give us some free memory. If there is free memory, or if we did that, then we can afterwards load the page into memory. That's the basic flowchart that we now need to implement for swapping. It's just a few steps that we need to add to this page fault handling. The other part for swapping is that we need to write to the disk. The swap device, here it says virtual memory, but we mean the swap device here, is located at the third partition of the first HDD by default in your swap. Right? We're talking about the exercise here, so this is specific to swap. And the block device number is 3, and the responsible code is in these Arch BD classes, Arch block device classes. In the chat, there's a comment, I don't see the case for if the reason for the page fault doesn't exist anymore. Yes, some of these cases in the flowchart might not apply for the specific swap implementation that you have, but depending on how you implemented it, this might be relevant or not, some of the nodes. Let's talk about this simple example here. We take the block, which is a size t, and page data pointer to the source data, and we can simply write to the disk, similar as with the write sys call, by just passing it to this block device class, block device object. We get the device by number 3, then we use the write data method. We write to this location block times the block size, so the block number, similar as a page number, right? Block number times block size, and then we want to write out one page of data, and here is the page data, the pointer to the source data. Please do not use BD request directly. This is a wrapper that takes care of the more dangerous parts. Using BD requests directly is unsafe. You can do more things with that, but it's unsafe if you are not absolutely sure what you're doing. The next question, and we can go through another round of brainstorming there, there we before we do that, I will answer this question from the Menti. What exam questions can we expect? Only assignment 1 relevant questions, or also assignment 2 relevant questions? So topics that you will work on in assignment 2 will also be part of the assignment 2 exercise interview, not assignment 1 exercise interview. So for instance, swapping would not be a question for the first exercise interview. Which pages are swappable? Let's maybe brainstorm this. What can you swap? What types of pages? What pages? What do you want to swap out? The stack pages, okay. User space pages, all user space pages. Someone says only data pages, maybe. Only user space pages? Why only user space pages? What about code pages? Not data pages? Why not code pages? User space stack, data pages, user space pages. Kernel pages. Someone wants to swap kernel pages. Sure, you can do that. But I'm not seeing one suggestion here. Also, pages that you've worked with in the first assignment, pages that you have all worked with, where you store data, some special type of data. Guard pages, hopefully not guard pages, because guard pages are not present. They don't use any physical memory. We don't need to swap them out. Not the swapping code. Yes, if you swap out the kernel, everything, sure, you can swap everything except for the swapping code maybe. But something we haven't seen yet. What about page table pages? So let me summarize that a bit. User space pages. For which of those does it make sense? Data pages apparently was a candidate that you really liked, so that got a lot of upvotes. Code pages, maybe also think about what we can do with code pages, because code pages also consume a lot of memory. Maybe we can also do something clever there. But also, if we swap out all the user space pages that are mapped by one page table, then you can also mark the page table, page directory, or page directory pointer table as non-present and swapped out. Swap it out, why not? You save some memory, sure. Kernel pages, in SWAP, this has not been done before, but for instance, some operating systems like Windows, they do that, they swap out whatever they can, also kernel pages. Okay, let's take a look at the page table entries and see what we can do there. In the page table entries, we have the present bit at the top. You can see that here is 1 bit present, and if it's 0, then this entry is invalid and all the bits are ignored. That means the hardware does not use this entry anymore, and whenever you access it, when the hardware accesses it implicitly, then you get a page fault. That means this entry is 64 bits, right? 8 bytes. 1 bit we cannot use, but there are 63 free bits now for us. They are all ignored. Maybe we can store something clever there. Okay, what else can we do? Writable. If we set writable to 0, then it's write protected. Then it's read only. That's here, the second bit here. We have the user space access bit. If it's user accessible, write through and cache disabled, that's for caching. Accessed and dirty. Accessed and dirty. If they are 1, then the page has been accessed or modified. Okay, these are the bits that we need for the PRA that we've already learned about in a lecture. And then we have the size bit, which defines whether we have a 4 kilobyte page or a 2 megabyte page on the lowest level, but on the higher levels also whether it's a 2 megabyte page or a 1 gigabyte page, or in the future at some point we will probably also support 512 gigabyte pages, depending on the layer where this size bit is set. The global bit, we will talk about that more. Then we have here ignored bits, ignored 2. There are 3 ignored bits here. These are unused bits, they are not used. And you can very nicely see that if you sum this up together, up to this point, these are 12 bits. We have 4 kilobyte pages and 12 bits up to this point where the page number starts. Because if you take the physical address divided by the page size, then you get the page number. So if you take these bits for a different purpose, then you have the page number in here. If you look at this and would zero out all these bits here, you would have the physical address of this page, the start address. This is very nice. So we have 3 ignored bits here, but we also have more bits here. Reserved and ignored, 11 more bits here, and execution disabled down there. So that means we have a lot of bits that we can reuse for our own purpose. And there's just one thing that we ask you, because we see that every year in 1 or 2 groups. Don't use ignored bits without renaming them. It's super confusing if you see in the code somewhere a line like ignored 2 equals 1. The value is ignored. Why are you setting it to any value if it's ignored? So please rename it. Okay, what else do we have? The physical page number. This is the largest part of this page table entry, and you can see here it's 28 bits. plus 12 bits of offset, so we support up to 40 bits of physical address space with this page table entry. Okay, the page number, the physical page number, we don't have that while the page is swapped out, right? Interesting. Maybe we can do something with that. The next part is, so we've already talked about in the lecture how to swap out or how to select pages to swap out, but we will also talk about that in 1 or 2 slides later. We talked about how to write to the disk. We talked about which pages to write to the disk, but also we need to talk about how do we get to this situation? How do we test this? How do we use lots of RAM? Because if I want to create a large array on the stack overflows immediately because the stack is just too small. It can't be used to exhaust the memory. So how do we do that? With big arrays, big number here. And where are these arrays? Of course, they are in a global scope because the stacks might be size constrained. So we want to create global arrays with a big number here. And with a big number, I don't mean something like 10 or 100, but use numbers like 1,000,000. You should test all swapping situations, and that without running into the limits of the kernel heap. So it's also not a solution if you say, okay, I create a lot of threads and they will use a lot of memory. Yes, but it will first get you out of kernel heap because the kernel heap is quite small. So you want to test this without running into the kernel heap. But of course, also with multi-threading, because if you test this only single-threaded in a single-threaded way, you might not find your race conditions. So you want to test this with multi-threading, with multiple processes. You want to use fork or exec while some of the pages are swapped out and see what happens, whether your operating system can work with that. Yeah, free memory can exhaust very soon, even if you implement a very, very good page replacement algorithm. And there is a very nice trick how you can exhaust the memory very fast. And maybe I didn't prepare a brainstorming slide for that one, but maybe you can write it in the chat how you would exhaust the memory as fast as possible. With this array. If I ask the question differently, which I know I shouldn't do because you need some time maybe to think. Yeah, to which indices would you write? And there's already one proposal here in the chat, and you can see it's write 1 byte per page. Yes, 1 byte per page is already nice, but I would actually write more than 1 byte. Maybe write something like 4 or 8 bytes per page, because that's not really slower. It can even be faster. Yeah, you would only write to 1 offset per page. If you write something like 8 bytes, can you write to 2 pages at the same time with a single operation? Yes, if you choose the right offsets in this array. Malloc, yes, Malloc, you can also test swapping with Malloc, but I would definitely recommend also test it with global arrays. Okay, let's see whether the cat wants to come in. Yes. Okay, and then we continue with the next part, the PRAs. The PRAs, the page replacement algorithms, there it's all about which pages should be evicted. So which pages should we kick out? And the question then is, yeah, of course, what it does, we know that from the lecture. Usually we run the PRA when nothing is to be done or when we need memory and we can't do anything if we don't get the memory. But we don't run the PRA all the time. It's not permanently running, so the system is not slowed down by that. The question is which PRA? And we recommend in general aging or working set random. That's a good algorithm that you can start with. And of course, you can implement more PRAs and get more points for that. You can also design your own PRA. you know the principle of locality, and maybe you have a brilliant idea how to use the principle of locality in a new way, and how to get better performance than the other PRAs. If so, implement that and just compare the performance. You get bonus points if the user can switch between PRAs. You get bonus points for every PRA you implement, or actually there's some limit on how many bonus points you can get from that. We categorized the PRAs, and yeah, you can then get bonus points in each of these categories. Of course, if you write your own PRA, design your own PRA and argue why it doesn't fit into any of the other categories, then you will also get an appropriate number of bonus points for that. Some of these algorithms need time, not just computation time, but they also need to work with the timestamp. So where do we get this time information from? We have scheduler ticks, we have the timestamp counter, and we also have the real-time clock. These are different timing sources, and we can, for instance, recycle parts of the sleep or clock implementation here. For working set, for instance, if we implement something like working set clock or working set random, this would work with the process time, and there you would reuse parts of the clock implementation. For aging, you might want to work with interrupts, but we've already discussed this in a lecture where you would introduce this part of increasing the ages per page. Yeah, you can derive the time from any of these timing sources. In the interrupt utils, you might find code that you want to connect this to. Another big part in assignment 2, and this will probably be one of your performance bottlenecks, and probably the point where you run most often into locking errors. That's the inverted page table, IPT, inverted page table. Usually, we have a page table that maps from virtual pages to physical pages. Now, with swapping, there might be situations where we have a physical page, but we need to figure out which virtual page it is. And this is what the inverted page table provides us with. Let's assume we have shared pages, and yeah, maybe these shared pages, by definition, they are used by several processes, right? Or can be used by several processes. And that means that we have page table entries in different user processes that point to the same physical page. They have the same PPN in there. And the question then is, which pages can we share? And I've prepared another brainstorming on Menti for that. Oh, this is the, just ignore the prompt here. I tried to update this, but it didn't store the update apparently. So the question is up here, which pages can be shared? Or where can the pages be located? User pages, maybe? Code pages? We can share code pages, okay. But where are code pages? Are they in RAM? RAM and swap space? Okay, we can share pages in RAM. We can share pages in the swap space. Okay. Can we share pages somewhere else? There's one more option that I'm looking for. Copy on write, of course, this is also a big point. Copy on write pages can be shared. So again, this prompt here is, I made a copy paste error here. The prompt should be, where can pages be shared? And one option is missing, but I'll resolve that now. RAM, we can share all the RAM pages. We have that already with copy on write, and we can do that also for shared memory. Swap, pages that are currently swapped, but also pages that are in the binary. In the binary, we can also say, well, they haven't been loaded yet, but if they will be loaded, they will be shared memory and copy on write, for instance. Yes. That's related to copy on write. Let's take a look at this illustration here of shared memory. We have memory mappings from user processes, from virtual memory to physical memory, and maybe here's some shared RAM, but also some pages shared on the swap device. And now a single bit doesn't suffice anymore because we now need to know which processes are referencing this shared page. The same goes for the swap device. We need a list. We need a list of processes that reference this page. Yeah, virtual memory or swapping and shared pages. And here's the thing that we need to turn around, this inverted page table that connects a physical page or a swap page to all virtual page usages. If only one process uses a page, then it's super easy to swap out a page, right? We swap out the page and we inform the process, right? It's super easy to figure out which process owns the page because we know the page directory or the page table that we just modified. And so we know which process this belongs to. But if we have shared pages, then we have to swap out the page and inform all the processes that it's been swapped out. We now have to update all the arch memories, all the page table structures for all the processes. And also the question, which processes are these? Which processes do own the page? Which have these pages mapped? So you need some form of mapping there. And also what happens if a process terminates and a page might be swapped out or a page might be shared. We have to be careful to update this inverted page table correctly. So this is a crucial part of assignment 2, and it will keep you busy probably through the entire task to have an inverted page table that doesn't suffer from locking problems and that is working correctly. Let's talk about copy on write. Copy on write was already part of assignment 1, but in assignment 2 it changes so much that we give you the points for copy on write again, because you will have to change a lot of things. So copy on write, how does it work? Well, we have our fork system call, for instance. We fork the process, so we copy all the pages. The child process uses exec right afterwards, and the copying was completely useless because it's being deleted right afterwards. Do we really have to copy all of that? We discussed this in the lecture already. We could also make them use the same physical and swapped pages. So this changed now. Now it's also swapped pages. And 2 or more processes can now have the same pages in RAM or on the swap device, and we mark them as read-only. And if the process tries to write to them, then the process gets a page fault. Yeah. So they are read-only. We can set them read-only because we've seen the bits in the page table just before. The writable flag has to be set to 0. Then we get a page fault, and then the question is, what happens next? We check whether it's a shared page. Maybe it's a shared page that is read-only and not copy on write. But maybe it's also shared and copy on write. If it's copy on write, then we copy the page and link the new page into this page table so that we then write to this new page. Only one process is left, then actually we don't need the shared page anymore and we can just write to it. And I have this flow chart here. This is also a very old flow chart that we've used in the operating systems lecture, and it's not entirely correct. And I think we've discussed that already in the part on copy on write, but I will go through this again. Is a page present? It's the first check when we run into a page fault. If it's not present, well, then we already talked about this logic here. Then, of course, we check whether we can load the page from the disk and so on. Maybe it's a swap in, etc. If the page is present, then we are talking about probably a copy on write page fault, or a page fault where a page should not be writable. For instance, a read-only page. Maybe it's a read-only error where someone tries to write to a read-only page. Then in this case, if it should not be writable, then This is an error. Here it says, what if is the page global or shared? What does that global mean? I mean, I saw the global bit before. So we have to think about this global bit a bit more. If it's global or shared, then if the reference count is larger than 1, then we mark it, or if it's not larger than 1, if it's 1, then we mark it as writable and unmark the global flag. Here's the global flag again. Let's say the shared flag, shared or global flag, shared flag maybe. Mark it as writable and it's not shared anymore. Otherwise, if there are still more processes, then we have to copy the page, update the page tables, mark it as writable, and also unset any flags such as shared, for instance. And yeah, we decrement the reference counter of this physical page, so the next process might already be in a different situation here. Copy and write is very important, so this is the second mandatory task. We have swapping and copy and write. These are the mandatory tasks for the second assignment. And one question here about the global flag. I think we discussed this already, so if you already know the answer, feel free to answer the questions very quickly. What about the global flag? Global, what does global mean? Well, first of all, don't use it. Global actually means keep over next context switch. Wait a second. So how do you get from this to this name? Keep over next context switch. I could have imagined a lot of names for that, but not global. Yeah, this is not what you want. It's definitely not for shared memory, and it will cause almost untraceable bugs, because that means that virtual addresses from your process will stay valid across the next context switch in the next process. Addresses from your process will stay valid for the next process that has completely different virtual memory mappings, but now your virtual page is in the middle in there. This is really, really ugly and really difficult to debug. Rather, use one of the ignored bits, rename it, use that as shared bit instead. Copy and write, just a quick repetition. We already had this in the lecture. We have our physical memory in pages. Process A has a lot of pages, maybe a green, a blue, and a red page. They are somewhere in the physical memory. We fork. Process B now needs the same pages, and they share these pages in the physical memory now. Now, if process B tries to write to this page, maybe wants to color this page with a different color, maybe violet, and then it needs to be copied by the operating system, and then the write access can succeed. And now the page has a different color. We can also do another magic trick. And we talked before already about the case where we share pages in the binary. Copy on write without fork. Of course, when you start user shells web twice without fork, you could still share pages. You load the same image in different programs, or maybe in a different scenario, you generate the same data in different programs. And with that, you get to different forms of page deduplications. Some of these are based on the file name or the file, the inode maybe. Some of them are based on the content of the page. Maybe if it's all zeros, then you deduplicate it with a one universal zero page, where you only have one of it in the entire system, and you deduplicate all the zero pages with this one. Or content-based page deduplication that we will look at now. And we've also covered that briefly in the lecture already. Content-based page deduplication, you again have two processes with these pages. They were started independently, and the operating system will now scan through the physical memory with a deduplication thread and scan for pages that have the same content. And if it finds such a page, it makes them copy on write. And then as soon as one of these processes writes to this page, they will get a copy on write page fault. So now you have copy on write without fork. That's already it for the mandatory tasks. We can continue with the additional tasks. And there we have shared memory. Shared memory, we want to share the page between two processes so that they can work together on this memory or communicate with each other. And there's a simple scenario here that we can discuss. Process A wants to share 3 pages with process B. Process A performs a syscall to do that. So it says, give me 3 pages of shared memory ID 4. So we have some ID. This is what we call a pseudo file descriptor. The kernel then maps 3 virtual pages, maybe on demand, maybe directly, depending on how many points you want to get, to the physical pages, maybe these. Process B can then later on also say, I want to get 3 pages of shared memory of ID 4. And then the kernel will map other virtual pages to the same physical pages. And with that, we share memory. A and B now share 3 pages of memory. How do we implement that? You've already used shared memory in SLP, and you already know the syscalls for that. This is SHM open to get a pseudo file descriptor, right? The return value was an integer. SHM unlink to close a pseudo file or to destroy a pseudo file descriptor. Then we have mmap to map a file descriptor, maybe a pseudo file descriptor, but maybe also a real file descriptor into memory. And munmap to unmap maybe parts, maybe the entire mmapped area. So we work with these pseudo file descriptors, and all the users of the shared regions will use the same pseudo file descriptor. munmap and SHM unlink should be used when the process ends, or they are called automatically then, or manually if you want to unmap and destroy the shared memory object. Otherwise, in some cases, for instance unlink, maybe you want the shared memory to survive the process lifetime, and in that case you might actually leak resources to, that the operating system doesn't know that you still want to, or the operating system assumes that you want to keep these resources, so it cannot just throw them away. If there's no reference anymore, with munmap or SHM unlink, you decrease the reference counter on the shared memory object. If there's no reference to the shared memory object anymore, then you destroy it. As I said, you can use the file descriptor here with a pseudo file descriptor from SHM open, but also with a real file descriptor, and that gets you to memory mapped file IO. You can just map a file into your memory, and you then can access files without open, create, close, read, write. We've seen that also in SLP, and instead you can use them very conveniently with pointer arithmetic. Parts of the file or the entire file is copied into the RAM on demand. You don't want to do that all at once because the file might be too large for RAM, but you want to on demand load things into the memory and write them also back dynamically, but at the latest when the file is being unmapped and the data has been modified, then you want to write it back at the latest. This depends, however, on the flags that you use when mapping the file. If you use map shared, then it's written back. Otherwise, it's not, but we will see that also on the next slide. If several processes map the same file, whether it's a pseudo file descriptor or a real file descriptor, then you get shared memory of a file or shared memory on a pseudo file descriptor. Just to go through mmap and munmap in a bit more detail, but we already remember this from SLP. The file descriptor comes from SHM open or open. Then the question is, how do multiple processes get to shared memory? Well, they know the path that they provide to open or SHM open, and they have the same access permissions, so then they can open the same file and mmap it. The length should be a multiple of page size, which probably makes sense to you because you can't map memory in something smaller than a page size. But what if the file size might not be page size aligned? You might have pages or you might have files that are smaller than 1 page, right? Maybe a file that is smaller than 4 kilobytes. So what do you do in this situation? You have to think about this case and then solve it in your implementation. Protection flags, we've seen prod read, prod write in SLP already. If it's a prod write protection flag, then the flags, these flags here, become relevant. We have map private here, copy on write, no write back, so the updates to the file are not performed. You only see them in your own memory. It's a copy on write mapping. Map shared means the changes are written back to the file, and other processes that are also opening the same file with map shared see the changes immediately. It's shared memory then. It's easy to combine this with shared memory syscalls, but also memory mapped IO. You get both of them basically together. It's not a lot of extra work. The next part is Malloc. Maybe you want to provide the user with more allocation techniques. Maybe you want to provide Malloc, for instance. And the question is, how does Malloc internally work? I think you already know that from SLP. And you can implement Malloc and free in operating systems and get points for that. A simple variant how to implement that, you have your code data BSS segments here, and the breakpoints here, and you increase it with the break syscall or the sbreak syscall, and that means that you then have memory that you can use to work on. For instance, like this, using the break syscall to get 4 kilobytes of more memory. A very simple implementation of Malloc and free. You can't directly use break and sbreak, right? They are complicated, but Malloc and free are very simple as well. Very simple to implement also in the libc. You might reuse your implementation from SLP. Malloc and free manage these regions that you, or this one region basically, the heap, and basically you place your Malloc segments in there. It will dynamically request the pages from the kernel, so whenever you need memory, you probably get a page fault and then a page is mapped there. But also unused pages will be freed, so if you then call sbreak and decrease the heap size, then these pages will also be released so that other processes can use them. Yeah, break and sbreak are used here. A very simple implementation will use a doubly linked list, and these elements in the list will contain the actual memory regions. So it's a struct plus some payload for the data. Here again, something that we didn't check in SLP, I think, was locking. You have to make your Malloc implementation thread safe. So this is something that you might have to add. And with that, we are already at the design and submission formalities. Okay, I see there are currently no questions in the chat, so we might have a lot of time in the end left to run through one of the examples. I would, if in the end we still want to run through an example, I would do that, however, on Discord, so that you can also more interactively ask questions. Actually, I thought, no, actually I said I shouldn't do that because we are already having exercise interviews, but we can run through the examples for the second assignment if you like, because we also want to practice those. Design and submissions. The proof of concept implementation works the same as in assignment 1, and we would recommend to start with swapping and then copy on write. You can also, this is technically possible, swap the mandatory tasks. The normal way is that you have virtual memory, so swapping and copy and write as the mandatory tasks. But if you want to go and do something else, you can ignore, or you can also do that. If you want to go the normal way, just ignore this slide. We will be through this in about 30 seconds. The alternative is that you can discuss with me what the alternative mandatory task could be. For instance, security or driver development. This is very rarely chosen because driver development gets very monotonous at some point. In security, you need a lot of additional knowledge to gain enough points on security. Driver development, I've seen that a few times, but in the end, the groups had enough points on virtual memory either way. So even if they implemented security, because security very often depends on virtual memory, driver development also in some parts needs some memory mappings, and usually the groups then get enough points on virtual memory either way. It's not possible to switch the mandatory task without discussing it with me. For the submission, how does it work? Same as in assignment 1, you tag this with submission D2 for the design proof of concept and submission I2 for the implementation. And then we have the deadlines. The deadline for the POC is the 22nd of May. So that's about, I think that's a bit more than 4 weeks from now. And you will have your individual feedback meetings between the 24th and 28th of May, ideally. The implementation deadline is then a bit later in June, on 18th of June. That's approximately in 8 weeks, I think. And since 2011, we went to a pub after the implementation deadline, except for the last semester. It was not possible last semester to go into a pub after the implementation deadline. Maybe, depending on how far we are with the vaccination and everything, maybe we can go and have drinks on the 18th, but maybe also not. And if it's not possible on the 18th, we will do that later in the summer when people are vaccinated and we can safely do that. The student debates on the A2 designs are already in 2 weeks. So between 10th of May and 14th of May, they work pretty much like in assignment 1. We will again have a list of topics, and you will have to discuss with a few other students about these topics. There's a compulsory attendance, same as for the assignment 1 design student debates. And repeating the assignment specification is not enough. We had some students that were kicked out in the assignment 1 design discussions, so I would try to avoid that for the second assignment design discussion or student debate. As you've already invested a lot of time, and it would be not so nice to drop out this way. Your design should be complete by this time, but of course it's totally fine if the design changes there or afterwards. This is totally fine, but you should have thought about all the problems that you're confronted with. You will get instant feedback from the tutor and from the other students. And now I'm already at the very end of this lecture, and we've only used up 1 hour. In lecture hall, this usually takes a lot more time because for all of these questions, I try to solve them interactively with a discussion with the students. But of course, in the digital format, then the timings change a lot, where some parts take longer and some parts do not take as long because you cannot really have as much interaction with the students. In the end, we will have evaluations, and these evaluations are very important to us. We read them very carefully and try to improve things that we can improve. Tell us what you found good, tell us what should remain the same, and then tell us also what was bad and what should be changed. We want to change things, we want to improve things if there are things that we can improve. And I think every year we find something new that we can improve. For instance, the feedback from last semester was that the design discussions, the student debates don't work in the digital format as we have tried before in the last semester. We changed the format, and the feedback by now was that it worked a lot better and it was a lot easier to participate in these student debates than last semester. With that, we get to the Q&A. Let's check out the Q&A. Okay, what do we have? Can I do driver development just as an additional task? Of course, driver development is a great additional task. You can implement any driver you like. Popular drivers include sound drivers to play music on your SWAP. We had network drivers. They also have gotten very popular because with that you can more or less browse the internet from SWAP. Interesting. So, actually, I had this Q&A, this question, but I somehow missed it. Okay. So let's. What is this? Is this an overview of the Q&A? That's a bit odd. I don't know where this one is coming from. So without substituting the mandatory tasks, definitely possible. Also, security tasks are very popular. So many students will implement some security aspects into their SWAP, some security features. Okay. Drinking a beer with you would be so nice. Yes, I would also like going for a beer with all the students and having a very nice evening. And how many points for programming is CSGO so that you can be a top fragger on Saturday? CSGO hack. If you make CSGO run on SWAP, that of course would involve so many kernel features that you would be far above the points scale. So that would definitely be more than we ask for. So CSGO supporting a game like that on SWAP would be really, really cool. What will be the topics in the student debates? I have to check where I can hide this one. Yeah, okay, this worked. What will be the topics in the student debates for A2? The topics for the student debates in A2. We will send them out via email, I guess, and there we will inform you what the topics are. I think we did that also last time for the student debates for A1, that we sent out the list via email. I guess the topics will be how to manage the swap device, how to write to it, how to manage it, how to select which page to swap out. So how you organize that in code, not just theoretical, what does the PRA do, but how do I actually implement that in SWAP, in this source code base. We will definitely have a discussion about copy on write. We will have probably one person from each group discussing the inverted page table. We will probably have some people talk about shared memory, memory mapped IO, Malloc. Those are probably the tasks that we are going to discuss in the student debates. First impression of A1 submissions, a lot of points. Was my first impression. Yeah, there are a lot of points that students got here. And with that, we are basically at the end. And at this point, this is the last lecture. And I want to thank you all for being here. And I hope that you enjoyed the lecture, learned something, and maybe we see each other for a bachelor thesis, for a master project, for cloud operating systems as a follow-up, or maybe in side channel security later on in the masters. So maybe we see each other in another lecture. I would really like to, and then probably also in person again. And with that, I would like to close and thank you for your attention again.